For pathfinding, we start by computing all possible Hamiltonian paths. For every path, we calculate the total Euclidean distance traveled, and ultimately select the shortest path. Once the optimal order of obstacles is determined, the robot uses the modified A-star algorithm to find the best path from its current position to each goal, considering movements such as forward, backward, forward left, forward right, backward left, and backward right, with all turns restricted to 90 degrees. The path cost function includes all forward, reverse, and turning costs of the robot from its starting position to its current position. The heuristics function is the Euclidean distance of the robot's current position to the goal node, which are the arrows in front of the obstacle. The black boxes are the boundary of the 2x2 meter area and also the boundary of the obstacles, meaning the robot cannot travel inside these boxes to prevent the robot from going out of bounds or going too close to the obstacles.
Okay, let's talk about RPi. The RPi is the brains of the entire operation and controls the entirety of the board. Our RPi uses standard serial connections for communication with Android and STM32. TCP is used to connect to a PC where the pathing algorithm is hosted. A separate Bluetooth thread is created to facilitate real-time responsiveness to commands from algorithm. Whenever a new image recognition model is detected and loaded, the RPi will convert it to NCNN first to allow for significant time savings. A HTML server is created by the RPi at the end of the run, and the image is stitched together for easy presentation in any web browser, bypassing frustrations caused by long load times and unstable connections.
My name is Raghav Singhal and I worked on the image recognition part for the MDP model. I clicked several pictures of all the alphabets and the numbers from various angles and various lengths, and I also tried to incorporate different lighting while taking the pictures. Then I used the YOLO V8 model to train the images. I used RoboFlow to upload them, and then I annotated on RoboFlow itself. And the resulting product was that whenever we used the RPi camera, it gave us certain IDs, which were then passed on to the algo team to decipher and use for the MDP robot movements.
Communication between the STM32 board and the Raspberry Pi was carried out via UART. In task 2, we used two sensors. The ultrasonic sensor measured the distance to obstacles in front, and the IR sensor was used to detect the edges of obstacles beside the vehicle. This allowed the vehicle to stop precisely in front of obstacles and turn without colliding with them.
Hi, my name is Glendon. For my part, I mainly focus on completion of task 1 as well as configurations of the pins and FreeRTOS. So for task 1, firstly I set up the gyroscope and encoder to allow accurate turning and traveled distance. So while the gyroscope is rather accurate, the distance traveled is not consistent, especially when a robot is traveling for long distances. And so I implemented a PID controller to correct this error. And then these implementations are then combined into two main functions, turning drive and move distance, to complete the movement of the robot.
For the Bluetooth functionality of the app, you can view already paired Bluetooth devices as well as connecting to new Bluetooth devices. Once the tablet is connected to the Raspberry Pi through the app, it can send string commands to the Raspberry Pi to enable movement of the robot.
Our app has a very simple interface that's easy to use. On the home screen, you'll be able to drag and drop obstacles onto the grid map, as well as change the directions it's facing by pressing the Set Direction button and tapping on the obstacle. To clear the entire map, all you have to do is press the Reset button. There are some available presets that you can choose from for extra convenience as well. To begin a task, you can press the Start button to send the coordinates of the obstacles on the map to the RPi to run the task. When an image is recognized, the number of the corresponding object will change to the ID of the image detected. You can also see the change in the target captured message box. To see the full details of the message, you can switch to the messages page to see commands received and sent.